Dino the Differential Dinosaur here, talking to you about AP questions involving differential equations. Now here's a question. What did dinosaurs put on their ice cream? Triceratops!
First, we're going to do a quick review before we get into the questions about how to solve differential equations. So the first step and the most important step is to separate the variables. Make sure all the x's get to one side of the equation. Make sure all the y's get to the other side. Make sure all the t's get to one side. Make sure all the w's or whatever get to the other side. Then, after you do that, you're going to move on to the second step, which is to prepare both sides for integration. Meaning, if you're integrating a function with multiple terms, you're going to integrate each term separately. If there's a function being multiplied by a constant, you're going to take that constant, move it out front of the integral sign. Once you have prepared both sides for integration, you can move on to the next step where you actually integrate and add c. After you do that, you have found the general solution to your given differential equation. But you must always check in step 4 if an initial condition was provided. If it was, you can use that initial condition to solve for your c value and find your particular solution. Now, on the AP test, here's how points are rewarded for solving differential equations. In questions that ask you to find the particular or general solution to a differential equation, you will get 0 points if you do not separate the variables. I've been saying this whole chapter, trying to instill this in you. You must separate the variables. It's the most important step. If you don't do that, you will get 0 credit for this question on the AP test. The second most important thing on the AP test when you are solving a differential equation is to add c after you integrate. If you forget to add that constant of integration after you integrate, you can only get half points for this question on the AP test. Please remember, separate your variables, and when you integrate, add c. Now question 1 says, consider the differential equation dy dx is equal to y squared over x minus 1. So there's 3 parts here. We're going to take each part individually. The first part says, on the axis provided, sketch a slope field for the given differential equation at the 6 points indicated. So if you ever get a question like this on the AP test where you're tasked with sketching a slope field for a given differential equation, you should be so happy. These are the easiest points you're going to get on the whole test. All you have to do is plug in each of these points, the x and y coordinates, to this given differential equation, and that will give you the slope of your general or particular solution, your solution curve at that given point. Then whatever that slope may be, you're going to make a little line segment going through that point with that given slope. So let's go ahead and do this. We'll start with the point 0, 0. If I plug in 0 for x and 0 for y in my differential equation up here, I get 0 over 0 minus 1, which is 0 over negative 1, which is 0. Meaning the slope of the line tangent to the solution curve at 0, 0 is 0. So through this point at the origin, I'm going to create a little dash that has a slope of 0. Next, I'm going to plug in the point 0, 1. So 0, 1 would be this point right here. If I plug 0 in for x, 1 for y, and simplify, I end up getting negative 1. Meaning the slope of the line tangent to my solution curve at this point, 0, 1, is negative 1. So I'm going to make a little dash going through this point that has a slope of negative 1. Next, I'm going to plug in the point 0, 2 to my differential equation up here for x and y. When I do and simplify, I end up getting negative 4. Meaning the slope of the line tangent to my solution curve at the point 0, 2 is negative 4. Now notice the slope of the line segment that I created at 0, 1 was negative 1. So if this slope is negative 4, it should be steeper than this slope. So I'm going to make a steeper negative slope up here. Now let's plug in 2, 0. So we're going to plug in this point to our differential equation. If I plug in 2 for x and 0 for y and simplify, I end up getting 0. Meaning the slope of the line tangent to our solution curve at 2, 0 is going to be 0. So through this point, I make a little dash that has a slope of 0. Next, let's plug in the point 2, 1. So I'm going to plug in 2 for x, 1 for y, simplify, and I end up getting 1. Meaning at this point, 2, 1, the slope of the line tangent to our solution curve has a slope of 1. So through this point, I'm going to make a little dash, a little line segment that has a slope of 1. Lastly, we're going to plug in the point 2, 2 to our differential equation. I'm plugging 2 for x, 2 for y, simplify, and I end up getting 4. Meaning the slope of the line tangent to our solution curve at the point 2, 2 is going to be 4. So through this point, I'm going to make a little dash, a little line segment that has a slope of 4. If this is what the slope of 1 looked like, then the slope of 4 should be a steeper positive slope. Sweet, I have successfully sketched the slope field for this differential equation. Part B says let y equal f of x be the particular solution to the given differential equation with the initial condition f of 2 is equal to 3. Write an equation for the line tangent to the graph of y equals f of x at x is equal to 2. Use your equation to approximate f of 2.1. Now you may initially think, oh, particular solution, I need to solve this differential equation. Let's go. Let's do the steps. No, read the question more carefully. It says write an equation for the line tangent to the graph of y equals f of x at x equals 2. So you're writing the equation for the line that's tangent to your particular solution. So in order to write the equation of a line, all you need would be a point and a slope to plug it into point-slope form. So is there a slope that we are given? Well, yeah, aren't we given the differential equation? Isn't that what this tells you? The slope of your particular solution at any given point? Yeah, so what we're going to do then is we're going to plug in the given point, our initial condition, 2, 3, to this differential equation. If I plug in 2, 3 to this differential equation and simplify, I end up getting 9 over 1, which is 9. Meaning the slope of the line tangent to your particular solution at the point 2, 3 is 9. So we have the slope, now we need the point. Well, we already know the point. It's 2, 3. So all we have to do is plug in 2 for our x sub 1, plug in 3 for our y sub 1, plug in 9 for our m, and we have the equation of the line tangent to our graph at x is equal to 2. Now on the AP test, when it says write the equation for a line, it typically wants it y equals. So you could just add the 3 to the other side and call it a day. That would be totally fine. You don't have to simplify on the AP test. Or if you wanted to put it into slope-intercept form, you could distribute the 9 and then add the 3, and you would get y is equal to 9x minus 15. So this would be the equation of the line tangent to your particular solution at the point 2, 3. Now we need to answer the second part of the question, which is to use your equation to approximate f of 2.1. So all you have to do is take 2.1 and plug it into the equation of the tangent line that you have created. So if I plug in 2.1 for x, all I have to do is just multiply that by 9, subtract 15, and I get that the approximate value of f of 2.1 is going to be 3.9. Now part C says find the particular solution y is equal to f of x to the given differential equation with the initial condition f of 2 equals 3. So now we're here. We made it. This is where it wants you to solve this given differential equation. So let's go through our steps. The first and most important step is to separate the variables. If you don't separate the variables, you can't get any credit for this question on the AP test. So we need to make sure that all the x's get to one side, all the y's get to the other side. So I'm going to multiply both sides by dx. That way these over here cancel each other out. And on this side, we now have both of the x's. Now we need to move this y squared to the other side of the equation, so we can either divide both sides by y squared or multiply both sides by 1 over y squared. Either way, these now cancel each other out on this side of the equation, and over here, we now have all of our y's. So we have successfully separated our variables. So we can move on to the next step, which is to prepare both sides for integration. So we're going to write an integral on each side, and look, are we ready for integration? Well, over here, we have 1 over y squared. Now, you may think, oh, that's just going to be ln of y squared. No! Remember, if it's 1 over y squared or 1 over y cubed, you need to rewrite this with a negative exponent. So this is going to be the same thing as the integral of y to the negative second dy. The reason is because now we can just use the general power rule. There's no ln involved. Over here, we have a rational function with a linear function in our denominator, meaning that this will require ln, some natural logs. So because this is just x minus 1 in our denominator, I could just integrate this and know that it's going to be ln of the absolute value of x minus 1 plus c. Or I could use u substitution just to be sure, make sure that I'm not forgetting any constants that are supposed to be there, and set u equal to our denominator. Then that means if I take the derivative of this with respect to x, I get du dx is equal to 1. Multiply both sides by dx, I get du is equal to dx. So I'm substituting u in for x minus 1, substituting du in for dx. Now all you have to do is just integrate both sides and add c. So on this side, we use the general power rule. We get y to the negative 2 plus 1 over negative 2 plus 1 plus c. On this side, the integral of 1 over u du is going to be ln of the absolute value of u plus c. Now please remember that we only put the c, the constant of integration, on the side of our independent variable. I know that both sides technically have a c, but if you subtract that c to the other side, a constant minus a constant is still just a constant. So we just leave this one constant over here. Now we simplify over here. This becomes y to the negative 1 over negative 1. And here we need to plug in whatever we set u equal to, which is x minus 1. So we take that, plug it back in for u. And now we simplify even further. Y to the negative first over negative 1. We can just rewrite as negative 1 over y. And again, we're solving for y. So we need to get y out of the denominator. So there's a couple things you can do. You can either multiply both sides by y and then divide both sides by ln of the absolute value of x minus 1 plus c. Or you could just take the reciprocal of both sides over here, then multiply both sides by negative 1. And now we have our equation y is equal to negative 1 over ln of the absolute value of x minus 1 plus c. This would be the general solution to our given differential equation up here. Now the question is, were we provided an initial condition that allows us to solve for c and get the particular solution? Yes, we were. We were given this initial condition, f of 2 is equal to 3. that will allow us to solve for this c value and get the particular solution. So let's do that. We take 3, plug it in for y. We take 2, plug it in for x in our general solution. We then simplify. 2 minus 1 is going to give you 1. ln of 1 we know is 0, and then 0 plus c is just going to be c. Now negative 1 over c, we need to solve for c, so we can take the reciprocal of both sides, multiply both sides by negative 1, we get c is equal to negative 1/3. So I can then take that negative 1/3, plug it in for c in our general solution, and we now have the equation of our particular solution to this given differential equation with this initial condition. Now on the AP test, they may not like having fractions within fractions, so if this were ever some type of multiple choice question and this didn't appear, what you could do is try to simplify this so there weren't fractions within fractions. You would just multiply the numerator and denominator here by the least common denominator in our denominator, which would be this 3. So if I were to multiply the numerator and denominator by 3 up here, it would just be 3. In our denominator, if I distributed the 3, it would be 3 times ln of x minus 1 minus 1. And that would be equivalent to this particular solution up here. Now question 2 says, consider the differential equation dy dx is equal to the quantity 3 minus y times cosine. Let y equal f of x be the particular solution to the differential equation with the initial condition f of 0 is equal to 1. The function f is defined for all real numbers. So this question has 3 parts. Let's take each part individually. First, it says a portion of the slope field of the differential equation is given below. Sketch the solution curve through the point 0, 1. So this time they're not even asking you to sketch the slope field. They're giving you the slope field and asking you to sketch the solution curve through this given point. So this is, again, super easy. This should be a free point right here. So 0, 1. Where's the point 0, 1? 0, 1 would be right here. We put a point right there. Now, we're going to sketch the solution curve. And remember, a slope field would just be a bunch of little tiny line segments that indicate the slope of the line tangent to your solution curve at any of these given points. So all we have to do in sketching our solution curve is just follow the slopes indicated in the slope field. So going to the right of our point, it looks like the slopes of the lines tangent to our solution curve start off positive but decreasing, and then around this x value they become 0, and then they become negative and decrease exponentially. On this side of our point, the slopes of the lines tangent to our solution curve start off negative but then start increasing until around this x value they become 0, and then they become positive and increase exponentially. So our solution curve should look something like this. Now part B says write an equation for the line tangent to the solution curve in part A at the point 0, 1. Use the equation to approximate f of 0.2. So again, before you get all excited about solving the differential equation, finding the particular solution, read the question more carefully. It says write an equation for the line tangent to the solution curve in part A. So you're writing the equation for the line that's tangent to your particular solution. So in order to write the equation of a line, all you need would be a point and a slope to plug it into point-slope form. Well, are we given a point? Yeah, we're given a point. It's 0, 1. Perfect. So all we need is the slope. Well, is there any way to find the slope? Yeah, that's what the differential equation is for. It's the slope of your solution curve at any given point. So all we have to do is plug in this point to our differential equation for x and y, simplify, and we end up getting the slope of the line tangent to our solution curve at the point 0, 1 is 2. Meaning, to create the equation of this tangent line, all we have to do is plug in 2 for our m, plug in 0 for our x sub 1, plug in 1 for our y sub 1. Now recall that on the AP test, they prefer to have your equation of your line where it's just y equals. So you could either just add 1 to the other side, or you could distribute the 2 and then add 1 to the other side to create slope-intercept form, and you end up getting y is equal to 2x plus 1. This would be the equation of the line tangent to your solution curve at the point 0, 1. Now we need to answer the second part of the question, which is to use this equation to approximate f of 0.2. So all we have to do is take 0.2, plug it in for x in that tangent line equation that we created, simplify, and we end up getting 1.4. That would be the tangent line approximation of f of 0.2. Now part C says find y equals f of x, the particular solution to the given differential equation with the initial condition f of 0 is equal to 1. So now we're here. We are going to find the particular solution to this given differential equation that passes through this point. So we go through our steps. The first step is to separate the variables. So we need to make sure we get all the x's to one side, all the y's to the other side. So we start with this dx. We're going to get that to the other side. So we multiply both sides of the equation by dx. Over here, the dx's cancel each other out, and we end up getting all of the x's on one side. Now we need to get the y's to the other side. side. So this 3 minus y, this quantity, we're going to move to the other side by either dividing both sides by 3 minus y or multiplying both sides by 1 over 3 minus y. Either way, these now cancel each other out, and we have all the y's on one side of our equation. So we have successfully separated our variables. Now we can move on to the next step, which is to prepare both sides for integration. So we're going to integrate both sides here. Over here, we're ready to integrate. Integral of cosine of x dx is just going to be sine x plus c. On this side, we have 3 minus y. Now, before you just integrate this and put ln of the absolute value of 3 minus y plus c, you need to note that y in this case is negative, meaning that's going to affect what happens when you integrate. So we actually have to use u substitution here. I'm going to set u equal to this denominator here, 3 minus y. So when I find du, I just take the derivative of this with respect to y. So I get du dy is equal to 0 minus 1. I then multiply both sides by dy. I get du is equal to negative 1 dy. We look at the problem. There is no negative 1. So what we have to do is we have to divide both sides by negative 1, move that to the other side. And now we can substitute in for this 3 minus y and the dy. So we take u, plug it in for the 3 minus y. We take negative 1 du, plug it in for the dy. Notice, if you had just integrated, you would not have this negative 1. So please be aware, when there's some number, some constant in front of our variable here, you got to use u substitution. So now we're almost ready to integrate. We got a constant here that we can move out front of our integral sign. Now we're ready to go. So we're going to integrate both sides and add c. The integral of 1 over u du is just going to be ln of the absolute value of u plus c. Distribute that negative, you get negative ln of the absolute value of u minus c. And then over here, the integral of cosine of x dx is going to be sine x plus c. But again, we only put the c on the side of our independent variable over here because technically a constant minus or plus a constant is still just a constant. So we leave that over here. Now we need to plug back in whatever we set u equal to, which is 3 minus y in this case. And now, is there any way we could solve for y? Yeah, we need to first get rid of this negative, so we're going to multiply both sides by negative 1. Remember over here to distribute, and then we need to get rid of the ln. So how do we get rid of ln? Well, we need to take the e of both sides. On this side, e to the ln. Those two things cancel each other out. That's why we did it. On this side, we need to simplify this somehow. So we need to use one of our properties of exponents, which says when you multiply like bases, you add together the exponents. So this is technically e to the negative sine x times e to the negative c, because if you multiply like bases, you would then add together those exponents. So we're going to rewrite it as e to the negative sine x times e to the negative c, but we're going to take that e to the negative c and move it in front. That way we can then drop these absolute value bars, put a plus or minus over here, and we now know that plus or minus e to the c is just a constant being raised to a constant, and plus or minus a constant being raised to a constant is still just a constant. So this whole thing can just be rewritten as our constant of integration, c. Now we can solve for y by subtracting 3 from both sides, multiplying both sides by negative 1, and we end up getting y is equal to c e to the negative sine x plus 3. This would be our general solution to this given differential equation. But this question wants us to find the particular solution. So we need to solve for c using this given initial condition. So we're going to take 0, plug it in for x in our general solution, take 1, plug it in for y in our general solution. We can now solve for c. E to the negative sine of 0, what's sine of 0? That's 0. And e to the 0 we know is 1. So 1 times c is just c. We then solve for c by subtracting 3 on both sides. We get c is equal to negative 2. So we're going to take negative 2, plug it in for c in our general solution, and we have now found the particular solution to this given differential equation with this initial condition. Now question 3 says consider the differential equation dy dx is equal to 2x minus y. So we have 4 parts here. First part says on the axis provided, sketch a slope field for the given differential equation at the 6 points indicated. So anytime you're given a question where you're tasked with sketching a slope field for a given differential equation and they give you a certain amount of points, you should be so happy. It's so easy. All you have to do is just plug in the coordinates for each of these points into your differential equation, get the slope that goes with them, and then create a little dash that has that indicated slope. So let's plug in each of the coordinates for these points in our differential equation. We'll start with the point 0, negative 1, this point right here. If I were to plug in 0 for x and negative 1 for y in our differential equation up here and simplify, I end up getting dy dx is equal to 1, meaning the slope of the solution curve as it passes through this point would be 1, meaning the slope of the line tangent to our solution curve at this given point is 1. So I'm going to create a little dash that has a slope of 1 that goes through this point. Next, we're going to plug in the point 0, 1, this point right here. So we plug in 0 for x, 1 for y in our differential equation up here. We simplify simplify, we end up getting dy dx is equal to -1, meaning the slope of the line tangent to our solution curve as it passes through this point would be -1. So I'm going to create a little dash that has a slope of -1 that goes through this point. Next, we're going to plug in the point 0, 2. So I plug in 0 for x, 2 for y in our differential equation. Simplify, I end up getting a slope of -2, meaning the slope of the line tangent to our solution curve as it passes through this point is going to be -2. So I'm going to create a little dash that goes through this point that has a slope of -2. And if this segment has a slope of -1, then the slope of -2 should be steeper and more negative. So it's going to look something like this. Next, let's plug in the point 1, -1. So that would be this point right here. If I plug in 1 for x, -1 for y, and simplify, I end up getting 3, meaning the slope of the line tangent to our solution curve as it passes through this point is going to be 3. So I'm going to create a little line segment that has a slope of 3 that passes through this point. And if the slope of this line segment is 1, then the slope of 3 should be steeper and more positive. So it looks like that. Next, let's plug in this point 1, 1. So we plug in 1 for x, 1 for y in our differential equation. Simplify, we end up getting a slope of 1, meaning the slope of the line tangent to our solution curve as it passes through this point is going to be 1. So I need to create a little line segment that has a slope of 1 that passes through this point. And if this line segment also had a slope of 1, you want to try to match that up. So it's going to look something like this. Lastly, we're going to plug in this point 1, 2 to our differential equation. We plug in 1 for x, 2 for y. We simplify, we end up getting dy dx is equal to 0, meaning the slope of the line tangent to our solution curve as it passes through this point is going to be 0. So we create a little line segment that has a 0 slope that passes through this point. We are done. We have created our slope field. Part B says find the second derivative in terms of x and y. Determine the concavity of all solution curves for the given differential equation in quadrant 2. Give a reason for your answer. So let's start with the first part of this question. It wants us to find the second derivative of our function. So how do you find the second derivative? You take the derivative of your first derivative. So we're going to take the derivative of our derivative. Now, when you take the derivative here with respect to x, over here it's just going to be the second derivative is equal to the derivative of 2x. The 2 hops out front. Derivative of x is just going to be 1. So 2 times 1 is just 2. Derivative of y with respect to x is going to be dy dx. You got to use a little implicit differentiation there. So now we have the second derivative of our given function, but it wants it in terms of x and y. So what we're going to do is instead of writing dy dx here, we know what dy dx is, right? Dy dx equals 2x minus y. So we're going to take 2x minus y, plug it in for dy dx, distribute that negative, and we end up getting the second derivative in terms of x and y. Now we can move on to the next part of the question that wants us to determine the concavity of all solution curves in quadrant 2. So how do we do that? Well, this question is just testing your reasoning skills. Do you know what happens in quadrant 2? Yes, in quadrant 2, we know all the x values are negative and all the y values are positive. So how does that affect your second derivative? Well, if I were to plug in a negative x value here, -2 times that negative would become positive, right? So it would be 2 plus something plus y, which we know is also positive, meaning there's no combination of x and y in quadrant 2 that you could plug in and get a negative second derivative. It would always have to be positive. Since your second derivative is always going to be positive in quadrant 2, we know that any and all solution curves in quadrant 2 would have to be concave up. Now part C says let y equal f of x be the particular solution to the given differential equation with the initial condition f of 2 equals 3. Does f have a relative minimum, a relative maximum, or neither at x equals 2? Justify your answer. So like we've said before you get too excited, like, oh, particular solution, let's go through our steps, let's solve this differential equation. No, read the question more carefully. It says, does f have a relative minimum, relative maximum, or neither at x is equal to 2? So where do relative minimum and relative maximum values occur? They occur at critical points, critical numbers, and critical numbers occur at whatever points cause your derivative to equal 0. So we just need to figure out at x is equal to 2, does this derivative equal 0? Well, we can plug in 2 for x, but what are we going to plug in for y? Well, we're given that initial condition, right? 2, 3, meaning at x is equal to 2, your function equals 3. So we're going to plug in 2 for x, 3 for y into our derivative up here, our differential equation, and see, does that equal 0? If it does, that means the slope of the tangent line to your solution curve equals 0, meaning there has to be a relative min or max value there. So we plug in 2 for x, 3 for y, we simplify, we end up getting dy dx is equal to 1, because the slope of your solution curve, or the slope of the line tangent to your solution curve at the point 2, 3 does not equal 0, it equals 1. F does not have a relative maximum or a relative minimum at x equals 2. Part D says find the values of the constants m and b for which y equals mx plus b is a solution to the differential equation. So normally what you would do to find the solution to this differential equation is you would solve the differential equation. You would separate the variables, you would prepare both sides for integration, you integrate both sides. But in this particular differential equation, we can't separate the variables. There's no way we can get all the y's to one side and all the x's to the other side. So how is this going to work? Well, this question involves a lot of reasoning. In this question, we're looking for two constants, m and b, for which y equals equals mx plus b is a solution to the differential equation. So we're going to solve for m first. We know m and b are both constants, and m is going to be the slope of your solution curve. So how do we find m? Well, aren't we given a differential equation? And isn't dy dx just the slope of your solution curve at any given point? So yeah, in this case, we know m would have to equal dy dx. M is slope, dy dx is slope. So those two things equal one another. So instead of dy dx, we're going to plug in m. Now, is there anything else we can plug in here? Anything else we know? Well, we know y is equal to mx plus b, right? So let's try that. We're going to take mx plus b and plug that in for y here. When we do that, we can then distribute that negative to the mx and to the b. Now again, we're just trying things out. We're trying to figure out what m is equal to. So how do we figure this out? Is there anything else we can do? Well, each of these terms right here has an x. Let's try to factor that out. So now we see that m is equal to 2 minus m, the quantity, times x minus b. So in this equation, this side of the equation does not have an x. This side of the equation does have an x. Meaning, in order for this over here to equal this over here, the coefficient for x would have to be 0, because otherwise there would be an x on this side of the equation. So what we're going to do is we're going to take this coefficient of x, 2 minus m, we're going to set that equal to 0 and solve for m. So how do we do that? We just add m to both sides. We get m is equal to 2. So m has to equal 2. Perfect. We got one of our variables. Now we need to find b. So how do we find b? Well, let's take this equation that we had right here. M is equal to the quantity 2 minus m times x minus b. If we know that m is equal to 2, we can plug in 2 here and here. And now, we got an equation with x and b in it. So how do we solve for b? Well, technically, this quantity, 2 minus 2, is going to be 0. And 0 times x, that's 0. So it cancels out our x. Perfect. So 0 minus b is just going to be negative b, meaning b has to equal negative 2. Sweet. We have found m and b so that y equals mx plus b is a solution to this given differential equation. Now question 4 says that time t equals 0, a boiled potato is taken from a pot on a stove and left to cool in a kitchen. The internal temperature of the potato is 91 degrees Celsius at time t equals 0, and the internal temperature of the potato is greater than 21 degrees Celsius for all times t greater than 0. The internal temperature of the potato at time t minutes can be modeled by the function h that satisfies the differential equation dh dt is equal to negative 1/4 times the quantity h minus 27, where h of t is measured in degrees Celsius, and h of 0 is equal to 91. So we have 3 parts of our question here. Let's take each part individually. The first part says write an equation for the line tangent to the graph of h at t equals 0. Use this equation to approximate the internal temperature of the potato at time t equals 3. So again, don't get too excited right away and try to solve this differential equation. It says write the equation of the line tangent to the graph of h at t equals 0. So we want the equation of a tangent line. In order to write the equation of a line, we need a point and a slope. First, how do we get a point? Well, I'm pretty sure in this question we were provided some initial condition at time t equals 0. Yeah, it says h of 0 is equal to 91. So in point slope form, to get our x sub 1 and y sub 1, that's just going to be this point right here, 0, 91. So we're going to plug in 0 for our x sub 1, 91 for our y sub 1. So the only other thing we need is the slope. So how do you find the slope of this function? Well, that's what our differential equation here is for. That gives you the slope of the function at any given point. So if we want the slope of our function at time t equals 0, we're going to plug in 0 for t. Oh, there is no t. Then we're just going to plug in 91 for our h. We simplify, we end up getting h prime of 0, or the slope of our function at time t equals 0 is going to be negative 16. So I can now take that negative 16, plug it in for m over here, our slope, and now we have the point slope form of the equation of the line tangent to h at time t equals 0. But on the AP test, they usually like you to solve for y, so you can either just add this 91 to the other side and call it a day, or you could distribute the negative 16 and then add the 91, and you end up getting the slope-intercept form of the equation of the tangent line to your graph of h at time t equals 0. Now we can answer the second part of the question, which wants us to use this tangent line in order to approximate the internal temperature of the potato at time t equals 3. So all you have to do is take 3, plug it into that tangent line for t, simplify, and you end up getting 43. Meaning the internal temperature of the potato at time t equals 3 is approximately equal to 43 degrees Celsius. Part B says use the second derivative to determine whether your answer in part A is an underestimate or an overestimate of the internal temperature of the potato at time t equals 3. So if you recall, when we talked about tangent line approximations, we talked about over or underestimates, where if your graph of your function is concave up at the point of tangency, then your tangent line will go underneath your graph, making your tangent line approximation an underestimate. If your function is concave down at that point of tangency, then your tangent line will go over your graph, making your tangent line approximation an overestimate. estimate. So we just have to determine, is the graph of your function h concave up or concave down at time t equals 3? Meaning, is the second derivative of your function h positive or negative at time t equals 3? So the first thing we need to do, obviously, is find the second derivative. So how do we find the second derivative of our function h? Well, we take the derivative of our first derivative. So let's take the derivative of this first derivative with respect to time, t. So when I take the derivative here, remember, this constant, negative 1/4, is just multiplied out front of our function. So we can take that constant, move it out front by the constant multiple rule, and then just take the derivative of what's on the inside here. So when we take the derivative of h minus 27, we're going to take the derivative of each term separately. The derivative of h with respect to t, we have to use implicit differentiation. You get dh dt. The derivative of 27, derivative of constant, is just going to be 0. So we get dh dt minus 0. We then distribute that negative 1/4. You just get negative 1/4 times dh dt. Now we want to rewrite this so it's in terms of h and t. We know what dh dt is equal to, right? It's equal to negative 1/4 times the quantity h minus 27. So we can plug that in here and then multiply these negative 1/4 out front. We get positive 1/16 times the quantity h minus 27. That is the second derivative of our function h. So again, how does this help us? Well, this is going to help us determine whether our tangent line approximation was an over or an underestimate. If the second derivative is positive, that means your original function is concave up at time t equals 3, meaning your tangent line approximation is an underestimate. If your second derivative is negative at time t equals 3, then your original function is concave down, meaning your tangent line approximation is going to be an overestimate. So how do we figure out whether our second derivative is positive or negative at time t equals 3? Well, there has to be some information in the question to help us figure that out. Well, it does say that the internal temperature of the potato is greater than 27 degrees Celsius for all times t greater than 0. That means for any time t greater than 0, the internal temperature of the potato, or h, has to be greater than 27. Meaning, if h has to be greater than 27 at time t equals 3, then your second derivative has to be positive. Meaning, your original function is going to be concave up on that given interval, meaning your tangent line approximation is going to be an underestimate. Now part C says for t less than 0, an alternative model for the internal temperature of the potato at time t minutes is the function g that satisfies the differential equation dg dt is equal to negative the quantity g minus 27 to the 2/3 power, where g of t is measured in degrees Celsius and g of 0 is equal to 91. Find an expression for g of t. Based on this model, what is the internal temperature of the potato at time t equals 3? So this seems pretty complicated because it's a long word problem, but it's really just asking you to find an expression for g of t, and it gives you dg dt and an initial condition. So all you have to do is find the particular solution to this given differential equation, and that will give you dg dt. So let's do that. The first step in solving a differential equation is to separate the variables. It's the most important step. You can't get any credit on the AP test if you don't separate the variables. So we need to make sure we get all the t's to one side, all the g's to the other side. So we're going to multiply both sides of this differential equation by dt. That way these dt's cancel each other out, and we have all the t's on the right side of our equation. Next, let's get all the g's to the other side. So how do we get the g's to this side? We're going to get this quantity, g minus 27 to the 2/3, to the other side of the equation. To do that, you can either divide both sides by g minus 27 to the 2/3, or you can multiply both sides by 1 over g minus 27 to the 2/3. Either way, these cancel each other out, and we now have all the g's on the left side of the equation, all the t's on the right side. This negative 1 is a constant. It could go on either side, but we typically leave it with our independent variable. So now we have successfully separated the variables. We can move on to the next step, which is to prepare both sides for integration. So we're going to integrate both sides of this equation. Now over here, this negative 1 times dt, negative 1 is a constant that we can just move out front of our integral. On this side, g minus 27 to the 2/3 in our denominator needs to come up to the numerator. And when we do that, we have to give it a negative exponent. Now the reason we do that is because we're now ready to integrate. And when we do integrate on this side, we just have to use the general power rule. So when we integrate g minus 27 to the negative 2/3, it's just going to be g minus 27 to the negative 2/3 plus 1 over negative 2/3 plus 1 plus c. On this side, the integral of dt is going to be t plus c. Distribute that negative, you get negative t minus c. Now again, both sides technically have a c, but since you subtract that c to the other side, it just creates one constant of integration, because a constant minus a constant, still a constant. So now we simplify this. Negative 2/3 plus 1 is going to be 1/3. Negative 2/3 plus 1 is going to be 1/3. We then know that dividing by 1/3 is the same as multiplying by 3. Now the goal here is to solve for g. So how do we solve for g? Well, we have to get rid of this 3. So we divide both sides by 3. We then have to get rid of this 1/3 exponent. So how do we get rid of a 1/3 exponent? Well, you're going to have to cube both sides of this equation. If you cube both sides of this equation, the 1/3 and the cube cancel each other out. That's why we did it. And now we just have g minus 27 is equal to this quantity to the 3rd power. Now we just add 27 to both sides, and we now have an equation in terms of g and t. Now, since c is still in our equation, this would technically be considered the general solution. But we want the particular solution because it gives us an initial condition. G of 0 is equal to 91. So that means we're going to take 0, plug that in for t, take 91, plug that in for g. And we can solve for c. So to solve for c, we just simplify this numerator up here. Negative 0 minus c is just negative c. We then subtract 27 on both sides, cube root both sides, and we get 4 is equal to negative c over 3. We multiply both sides by negative 3. We get c is equal to negative 12. So we take negative 12, plug that in for c in our general solution to make it our particular solution. And notice negative 12, when I plug that in for c, negative t minus negative 12 becomes negative t plus 12. Now I have successfully created an expression for g of t. So I can use that in order to find the internal temperature of the potato at time t equals 3. So we're going to take 3, plug that in for t in this function here, simplify, and we end up getting g of 3 is equal to 54. Meaning after 3 minutes, the internal temperature of the potato is 54 degrees Celsius.